I will be talking about UAV imagery automatic registration. And first of all, I wanted to explain a little bit about this problem and why these two words, multimodal and UAV. And I wanted to start with an example. If this works. Okay, now. So this is the area of interest. This is Dolak in Bosnia-Herzegovina. And for this application, we were providing UAV imagery for the mining applications. This was some of the main fronts during the war. So the areas marked in red are known minefields. And what they want to do is to have updated imagery from this area. So why UAV makes sense here? Because nowadays, I suppose you have all heard about UAVs for lots of applications, but maybe this kind of technology only makes sense for some very specific applications. So I will explain here the kind of, sorry, because this doesn't work. I think there is some problem with the mouse or something.
Are we on the second screen?
Change the. And now, well, maybe just clicking something. Press a lot. Okay. Okay. Okay, now it's working. Okay, so first thing is it's not working again. But the first thing is the low cost of these platforms. A system like this one you are seeing can cost only a few hundred euros. And with this one, you can carry any camera you are interested to acquire data. So in applications like this one, in which cost is very important because in this case, it's a kind of non-profit application. You are just trying to aid for an emergency in the area. You have to balance a lot the costs of acquiring that imagery. Also, the next thing is the resolution. If we want to be able to work with this kind of imagery, what we need is to have a lot of resolution in order to be able to properly define what are the areas that we have demined and what areas are not demined. For example, a day of work doing a demining action take the work of a demining of an area about 1 meter for 1 meter. So it's a very small area that you have to properly detect and mark in your data. And the next one, and maybe more important, is that flexibility of this kind of systems. With this kind of systems, from a ground control system, as you are seeing here, you can fly when you need it and plan the flight as you need it. So for example, if we have to fly during bad weather conditions, we can even fly because we will fly low without being affected by the clouds. Also, we can fly just at the moment as we need it, for example, just before and after the demining campaign. And at the end, what we have here is a kind of pocket satellite that you just pick it and throw it to acquire the images you require. So here you can see some of the images acquired in this application. Here is with the visible sensor. Here you can see that we have enough resolution in order to detect some land moves. In this case, the campaign was just after some floods that could move some of those landmine fields. And we can see just here, you notice this, and these are some landmarks that we can exactly see his extensions thanks to a resolution of around 5 centimeter pixels, or we even can work up to 1 centimeter pixels if necessary. Here you can see the same area, but now in near-infrared imagery. In this case now we can get information about the vegetation, the trees, what kinds of terrain we have here. For example, we can easily identify here some parts that are more rock. We can see the paths here, and also we fly with the thermal cameras in order to see artificial objects like power lines or all trenchers or things like that that can allow us to give more information to the mining teams. What's the problem we find with all this imagery is that if this wants to that we end up having multiple imagery from the same scene, but carried with different cameras. And as we are flying with this kind of small aircrafts that weigh around 2 kilograms, mainly for registration limitations and for ease of operation, we can only carry one of these cameras in each flight. So the problem we have here is that we want to merge all this imagery in the same reference in order to properly compare them, because each frame is giving us different information. So the traditional mode to do this is to retrieve the orthophoto mosaic, that is, do our flight with a certain overlap in order to, across some feature points, match all the images from each flight, and afterwards with the manual operation of the software we can add some manual points in order to co-register all the different mosaics, ending up having something like this, which you can see the background, the reference image, and here 2 different flags done in the area, one of the near infrared, another one for the visible camera. And you end up having a result like this one, in which you can see the matched final imagery, starting from the reference, in the middle the high resolution visible, and afterwards the near infrared image. However, this has some limitations. The first one is that it's time costly, because you have to do the mosaic from each flight, and afterwards also you need the manual points addition that has to be done by a person. So it has this kind of limitations that for some applications may not be enough. For example, if we are working for an emergency response in which we would like to have this practically near real time, it won't be enough. Also, you need to cover the region with this kind of overlap, so the production of all your flight is lower than if you could just take pictures of the single areas of interest. So what we wanted to start working is to try to find a way in order to register each imagery directly to the orthophoto we have from the reference. Here okay, now here we can see the problem we are facing. This is not in Bosnia, this is in Moya, where we have our headquarters. And you can see in the bottom the image from the Cartographic Institute of Catalonia, that is the reference we have there. And in the upper image is a near-infrared image acquired from a UAV. So the problem we are facing here is that we have different cameras with different bands and also different resolution that can be seen here from this false color representation. Also, we will have different flights. This was flown with manned aircraft, doing some of the campaigns programmed by the Institute, while the upper image is done by the UAV in a different flight. So you can see that the shades of the image are completely different, so we will have varying light conditions. And furthermore, we also have the problem that the orthophoto is a synthesized image. So we may find different artifacts. We may have also this kind of change of point of view. So for example, here out of being an orthophoto, you can see some faces. While here we are only seeing the roof. So doing this kind of registration is a kind of trick. So in order to proceed with the problem, what we done is we partnered in this project, the Computer Vision Center, that is from the Autonomous University of Barcelona, that has 20 years experience working with computer vision techniques, and also CAT UAV, that was the company I was working on, that has been working since 2000 with UAV, providing remote sensing and Earth observation services. So what we start doing when looking at this problem is searching for a good data set in order to properly evaluate it. And we found that there was no such data set available, so we decided that our main first effort was to generate this kind of data set so we can properly study the problem. And so we started working with the sensors you can see here. These are some of the mainly used sensors nowadays in UAVs. First is the Sonic UX Zoom, that as you can see is a very small camera with practically with visible camera with good resolution. Also with one of our near infrared modified camera that has the near band, the red and green. Also now we have just integrated the MicaSense, that is a multispectral camera that you can have the near infrared, the red edge, and also the 3 visible channels, but with a very narrow bands. It's a camera that is intended for agricultural applications. And also now we are also trying to integrate the new Tau2, so we can also get this thermal imagery. What we do after with this kind of image, we take imagery from a certain area, and the first thing we do is to generate a ground truth in order to properly evaluate the algorithms we want to test here. In order to generate this ground truth, it's pretty difficult to generate this in an autonomous way, mainly because in the UAV we cannot carry very widely systems. So what we decided to do is to just add a bunch of control points added manually in order to reference these glue points that we will know that are exactly the same positions in both the UAV imagery and the reference, and trying to find those points that we know that we won't be modified by the perspective. In this case, for example, we can see here a full corner in which we know exactly that this point will correspond to the other one, and it won't be effective for the perspective. This could even be rocks, signs in the floor, corners, or anything that we know that will be stable in time and that won't be modified by the perspective of the image. Next thing we done once we had this data set prepared is to prepare a little software in order to start trying the different approaches we think that may be useful. We started from the feature approach, and as you see, we have this small program in which we can select the data sets. We first have a detection step. After that, we extract the features of the points detected. After that, we do the matching using a nearest neighbor algorithm, and afterwards we transform the image after filtering with Landsat and doing the geometric transformation, doing an affine projection. If you run this kind of traditional approach directly to this problem, what you will have is that as we are trying to match a very small image to a very big one, you will end up having a lot of points across all the reference. So what you want to do is to try to focus your search only in the interest area. So we decided to use the information that we already have, that is the GPS and sensor information that the UAV is providing us. Practically all UAVs carry an automatic pilot on board, so GPS is always available, and sensor can have also, if you have a calibrated sensor, it provides you better information, but if you don't have it calibrated with only a rogue approach of each parameter, it's enough. Because what we can do with this is set the area of interest, so we just only search in the reference part of the image that we are interested in, being more effective in matter of time efficiency. And also we can rescale our imagery from the UAV, so it more or less has the same scale of the reference. Okay. This way, we are not so based on the problem of having this invariance with the points. In order to validate all the system, we just take some parts of orthophoto, put it, and simulated it. They work with the UAV, and done the matching in order to see that it was able to perfectly fit this kind of artificial approach. Once we had that, we started working with the city dataset. That is the first one that we have finished. That for the one has near-infrared imagery and visible imagery. And here you can see the reference, UAV image of visible, and near-infrared UAV imagery. And we started trying with the already implemented algorithms that are commonly used in computer science, mainly combining the detectors and descriptors in order to see if this kind of approach is enough to have some kind of first results. So, in order to check how well we're performing this kind of detectors and descriptors, what we decided to do is to plot the precision and the number of correctly matched points against the geometric error we are acquiring. This way we can have, from the very first beginning of the analysis, a clear idea of the kind of errors we will find. As you can see here, if we want to have enough precision in order to do a proper geometric transformation, we have to move to approaches in which we restrict the number of points we are matching, and we only pick the ones that are better fitted. So, for example, in this kind, we have ended seeing that working with surf work quite well, with having good precision and having some enough points, and providing errors around, theoretically, around 5 meters. Once we done the geometric transformation of this case, if I can now, we end up having this kind of registration. As you can see here, especially in the surroundings of the image, the error is a little bit bigger from the one we expected. Here, if you measure this, you will end up having the worst error around 50 meters. But in the best areas, it's around 3-4 meters. So although it's not a good precision error, it's enough in order for some kind of application, which like we were talking about, the emergency application, in which we will just want to locate some emergency points and not just to do a proper geometric transformation. Next thing we tried was the same with the near-infrared imaging, but as you can see, these kind of detectors cannot work well with this kind of images. They are too different in order to properly match them. So what we are now starting to study is to use more specific descriptors, such as ASIFT, that is specially designed for near-infrared imagery or thermal imagery, and also trying to work with a descriptor that has appeared from the Computer Vision Center that works in the frequency domain, finding more robust matches between this kind of so different imagery. Also, we are enhancing now the database that we hope that we will publish it during this summer. So if anyone is interested in also working in this program, we can provide this kind of data set that may be something that is difficult to find sometimes. And also we will be presenting all this in the workshop we are organizing this June in the Barcelona Drone Center. So just if anyone is interested. And that's all. I can finish this. So thanks and for your attention. If you have any questions.
Thank you very much. I think you answered one of mine. That was about the data, because you've got some very interesting data there. But you say it's going to be available soon in the summer, including the ground truth as well. So
yes.
Great.
Yes, we will put everything in a web so everyone can download it and start playing with it. Because one of our main goals that we are taking advantage of having these two labs, one from the university and one from the company, in order to generate this kind of data set and make it freely available.
Very good, very good. Okay, are there any questions? Sure.
It comes not really clear for me this error investigations you made. You compared photo from a camera central perspective, camera photo from the UAV with an orthophoto, which is a parallel projection. Typically, orthophoto has parallel projection. So the question comes up: the errors that you have comes from considering the terrain model in the orthophoto or not, but not from the camera, or from the matching. Could you explain how you make this error investigations not creating an orthophoto from the UAV? So it makes, from my point of view, no sense.
No. Okay, the error is evaluated from the ground control points we made.
Yeah.
What we do is generate this kind of manual control points that we know that it's exactly the same position. Yeah. With that, we get a transformation that will directly fit those points to the orthophoto. Yeah. And with that, what we can do is to evaluate afterwards how these points are reprojected from the final result to that one.
But that depends only on the height difference that you have in the terrain. The error depends on the height difference. If you have 1 meter height difference at the corner, you have probably 1 meter shift in the position. So if you're not considering the height situation, so how can you estimate the error?
Yes, because here we are talking only of the planar error. Yes. Yeah, I understand.
But if you have a different terrain, then you have different errors. Independently on your operators you use.
Yes, but in our case, we are working in a quite a small place of terrain. So if we are measuring those errors in as considering that this small part is quite flat, maybe we have variations of 10.
Oh, you have assumption of flat terrain.
Yes.
Okay.
Yes, because in our case, we want to match this just single part with the bigger one. So in most cases, what we will end up having is that variations in that specific scene are not bigger. And that is why also we pick the ground control points from the ground. We don't pick them from the roofs or the trees or anything that can vary because of the altitude and also the perspective that it will have. So at the end is the main idea of this kind of approach is not to have a thing to replace the orthophoto typical approach, but to have a thing that you just have some single images of an area and you want to have an approximate registration with the orthophoto. Specifically for this kind of images we want to work in the future, such as thermal cameras, that in some sensors you don't have enough resolution in order to properly work with orthophotos, because, or in the case that you don't have enough overlapping with the imagery. So yes, the error is not as precisely calculated as you are talking, but look at this more bigger approach.
Great. All right, thank you very much. In the interest of time, I think we should move on. But thank you again. Okay, so the final talk in this session is